In this video, we're going to discuss two particular types of functions, linear functions and the inversion function. So let's talk first about linear functions. The complex linear function takes the form f of z equals mz plus b, where m and b are complex numbers, not necessarily real numbers. So let's consider the example f of z equals 1 plus I quantity times z. So in this case, m is 1 plus I and b is 0. Let's compute f of 1 plus root 3i. So we take 1 plus I and multiply it by our input of 1 plus root 3 times I. I won't go through all the details here, but if you expand this and simplify, you get the following quantity. The result has a real part of 1 minus root 3, and the imaginary part is 1 plus root 3. Okay, that was simple enough. Let's look at another example. Compute f of root 3 over 2 plus 1 half I. So 1 plus I times root 3 over 2 plus 1 half I. If we expand and simplify, we get an output whose real part is root 3 minus 1 over 2, and whose imaginary part is root 3 plus 1 over 2. What we want to look at is we want to look at the geometric effect of f. So instead of just considering what f does to a point, what does it do to a particular region in the complex plane? Well, it's very convenient when we deal with functions that involve powers like z, z squared, z to the third, 1 over z, to do everything in polar coordinates. So let's first take our coefficient m and let's write it in polar form. 1 plus I, okay, I've plotted this in the complex plane. It makes an angle of pi over 4, so that's our argument. And the modulus of this is equal to the square root of 2. Because if you square 1 squared plus 1 squared and take the square root, you get root 2. So that means the polar form of 1 plus I is root 2 e to the pi I over 4. Now let's say we take our input, z, and write it in polar form as well. So z equals r e to the I theta, where r and theta denote the modulus and the argument of z respectively. Let's compute f of z. Now, doing everything in polar coordinates, here's my m value, root 2 e to the I pi over 4, and here's my z, r e to the I theta. And if we simplify a little bit, we get root 2 times r e to the I theta plus pi over 4. The modulus of f and argument of f of z are now root 2r, that's this part right here, and the argument is theta plus pi over 4. So that tells us that the geometric effect of f is to scale the modulus of a complex number by root 2 and rotate by pi over 4. So let's take a look at a particular example. Let's suppose that d is the set of complex numbers with the property that the argument of z is between pi over 6 and pi over 3, and the modulus of z is greater than or equal to 1 and less than or equal to 2. So what we want to do is we want to sketch d, and we want to sketch the image of d under the function f. Here's what d looks like. Here's the real axis. Here's the imaginary axis. So I want all the complex numbers whose arguments are between pi over 6 and pi over 3. So I'm going to put the origin right here. This is pi over 6, and this is pi over 3. This is now a distance of 1 from the origin, and this distance, this arc, has a distance of 2 from the origin. So this blue region represents all the points in the complex plane whose argument is between pi over 6 and pi over 3, and whose modulus is between 1 and 2. So that is our set D. Now what happens if we apply our linear function to everything in this region? What do we get? What does it look like? Well, we know from what we said before that the effect is to take every point in this region, scale its modulus by root 2, and rotate by pi over 4. So this is z1 and this is z2. We calculated their values a moment ago. F of z1 was 1 minus root 3 plus I times 1 plus root 3. So what we've done then is we've taken z1 here at this point, and here's its output, which is that point. Now f of z2 was root 3 minus 1 over 2 plus I times root 3 plus 1 over 2. Here is z2. What we've done is we've scaled its modulus by root 2 and rotated by pi over 4. So we get something like this. Now, the original angle was pi over 6 and pi over 3. Those were the original angles relative to the positive axis. If I rotate, then I'm adding pi over 4 to pi over 6 and pi over 3. And if you simplify the fractions, that means this angle is pi over 6 plus pi over 4, which is 5 pi over 12. And this angle is 7 pi over 12. It's pi over 3 plus pi over 4. So the image, if I take this little sector in the complex plane, and if I look at the image of that sector under the function f, I get something that looks like this. Now let's say we change things a little bit. Let's say we look at the same region in the complex plane, and now we want to sketch the image of D under f of z equals 1 plus I times z minus 1 plus 2i. So in this case, my m value is 1 plus I. My b value is minus 1 plus 2i. So we've already addressed this situation. Multiplying z by 1 plus I is going to scale the modulus by root 2 and rotate by pi over 4. So what does this part do? Well, the minus 1 is going to shift my result 1 unit to the left. 1 unit to the left, because the negative 1 is concerned with the real part. And then the 2i, because the 2 is the imaginary part, that's going to shift my graph up 2. So, in other words, this b has a real part of negative 1 and an imaginary part of 2. So that means I'll take the result of my preceding graph, and I will shift 1 unit left and 2 units up. So here's the origin here. What I've done then, focus that. Okay, that's the origin. So what I've done is I have taken every point here, and I have moved it 1 unit to the left and 2 units up. So for example, if I move, let's see, let me make sure I got that right. I'm going to take every point here, and I'm going to shift it 1 unit left and 2 units up. And so if I move 1 unit to the left, that means I will subtract 1 from this, so I'll have just minus root 3, and I will be adding 2 to that, 1, so I'll have plus 3. So the effect of taking the preceding graph and moving it 1 unit left and 2 units up is now I have this point right there, and I have this point right there. Okay, and then the origin is down here. So again, I took this result from the preceding, and I shifted everything in that region. I shifted that whole region one unit to the left and 2 units up. Sorry about the focus. Okay, let's look at a different type of function, the inversion function. The inversion function, f of z, is defined as 1 over z. We want to look at the geometric effect of this function as well. Well, let's compute f of 1 plus root 3i. This is the same z1 from our previous example. That would be 1 over 1 plus root 3 times I. Now, to write this in rectangular form, I need to multiply by the conjugate of 1 plus root 3i over itself, so I have 1 minus root 3i over 1 minus root 3i. If I expand this and simplify, and you might want to pause the video and do that to verify, you get 1/4 minus root 3 over 4 times I. Now, what about f of root 3 over 2 plus 1/2 I? So I have f of, I take the reciprocal of that, and again, if I take the conjugate of this and multiply this whole quantity by the conjugate over itself and simplify, this is a calculation you can do, you get root 3 over 2 minus 1/2 I. But what is the geometric effect overall of the inversion function? So let's say that z is equal to r e to the I theta for some angle theta. Then f of z would be the reciprocal, which would be 1 over r times e to the I theta. And I can rewrite this as 1 over r times e to the minus I theta. So if z has an argument of theta and a modulus of r, the resulting output will have a modulus of 1 over r and an angle of minus theta. So whatever theta is, we're going to be negating the angle. So the geometric effect of f is to first reflect z about the real axis. That's because if we take the original argument of theta, say theta was pi over 6, the argument of the output would be minus pi over 6. Now what does the 1 over r do? If r is greater than 1, then that means that r itself, z, would be outside the unit circle if its modulus was greater than 1, but its output would have a modulus that's less than 1. So z, if z lies outside the unit circle, f is mapping it to a point inside the unit circle. Now, on the other hand, suppose that r is less than 1, like r is a half or something like that. Then z lies inside the unit circle, and then 1 over r would be greater than 1, so f is mapping it to a point outside the unit circle. So let's go back and take a look at the same region. So this is a sector, the complex numbers, where the argument is between pi over 6 and pi over 3, and the modulus of z is greater than or equal to 1 and less than or equal to 2. What we want to do is we want to sketch the image of D under F. So again, here is that region. The origin is back here. This angle is pi over 6. This angle is pi over 3. Here's z1. It's 1 plus root 3i over 2. You can check yourself that the modulus of z1 is 2. This complex number, z2, root 3 over 2 plus 1/2 I, has the property that its modulus is equal to 1. So under the inversion mapping, we take each complex number and reflect about the real axis. So this point is going to be reflected about the real axis, as is this point right here. Now this point is outside the unit circle. It has a modulus of 2. So its output should have a modulus of 1/2. So f of z1 will be inside the unit circle. This point, z2, is on the unit circle. The output will have a modulus of 1 over 1, or 1. So a point on the unit circle will be mapped to a point on the unit circle. It will just be reflected about the real axis. So now the origin is up here. So f of z1 would be 1/4 minus root 3 over 4i. We calculated that a few moments ago. The modulus of that is a half. That makes sense. z1 had a modulus of 2. This has a modulus of 1/2. That corresponds to this point up here. On the other hand, z2, f of z2, is root 3 over 2 minus, oh, I got that backwards. Okay, so z1 was 1/4 minus root 3 over 4i. Its modulus was 1/2. So z1, which had a modulus of 2, was mapped to a point which has a modulus of 1/2 inside the unit disk. z2 was a point on the unit circle. This is f of z2, which we calculated a moment ago. Its modulus remains at 1. So again, the geometric effect of the inversion mapping is to take Z1. It was outside the unit disk. We map it inside the unit disk. If its modulus was 2, the output has modulus 0.5, and then we reflect this about the real axis. Z2 was on the unit circle, so its modulus was 1. The reciprocal of 1 is still 1, so f of Z2, this is Z2, will have a modulus of 1, and we're simply going to take this and reflect across the real axis. So here's the picture. Here's what I would like for you to do in preparation for class. So for each function below, compute f of Z1 and f of Z2 in exact rectangular form. That means evaluate all trigonometric values as well, and graph them along with f of d in the complex plane, as we did in the preceding examples. So in the first case, f of z would be iz plus 3, so here's m, and here's b. Let z1 be 1, z2 equals 1 plus I. Let d be the set of complex numbers whose real parts are between 0 and 1, and whose imaginary parts are between 0 and 1 as well. And this is really just the square in the complex plane that has corners at 0, 0, 1, 0, 1, 1, and 0, 1. And so what you'll see is that f of d will actually be a square, and it's going to be rotated, shifted a bit, something like that. Now let's suppose we look at the inversion mapping. z1 is 1/2 I, z2 is minus 1/3 I. Okay, so these points are actually inside the unit disk. Let d be the set of points whose moduli are between 1/3 and 1/2, and the argument of z is between minus pi over 2 and pi over 2. And this is a half donut in the right half plane, having inner and outer radii 1/3 and 1/2. So you want to look at the image under f of d as well. So please do these in preparation for class.